the way, how much time do I have? 1 hour? 50 minutes?
1 hour, Professor.
Okay.
So, if in the interactive session, you can take whole 1 hour.
Yeah.
Or if you want Q&A session separately, 55 plus 5.
Okay. Sounds good.
Good evening, everyone. Welcome to the Network Seminar Series hosted by the Center for Networked Intelligence at the ECE and RBCCPS IISc. It's my pleasure to introduce today's speaker, Professor Robin Rajamäki. He will be speaking on resource-efficient NextG MIMO sensing and communications, bridging sparse arrays, spatial modulation, and subspace codes. Professor Robin received his DSc degree in electrical engineering in 2021 from Aalto University, Finland. From 22 to 24, he was a postdoctoral scholar at University of California, San Diego. He is currently an assistant professor at Tampere University, Finland. His research interests lie in the intersection of theory and applications of statistical signal processing, optimization, and machine learning, with a focus on multi-sensor systems in sensing and wireless communications. Over to you, Professor.
Okay, many thanks for the introduction, and thanks for accommodating me at such short notice, and thanks to everybody showing up here on a Friday evening, and thanks Sandeep for hosting me. Okay, so yeah, as already said, the topic of today will be resource efficiency in future multiple input, multiple output sensing and communication systems. Okay, so to give a bit of background, basically with the emergence of future wireless systems, which are increasingly not only doing traditional wireless communications, but also sensing, right? This is a paradigm called integrated sensing and communication. The role of the array geometry becomes increasingly pronounced, okay? Because of the sensing channel is highly highly structured and dependent on the array geometry. So another aspect of these future so-called next generation NextG systems is that they need to be also make efficient use of their resources. And in particular, I refer here to spatial temporal resources, which include most notably the arrangement of sensors, or the sensors, right? Used in these typically base stations, for example, have antenna arrays. So they need to be they need to serve both the communications and sensing purposes, as well as then the actual signals transmitted from them. Okay, so this can be thought of as the waveform. I call it the waveform here, and it can be thought of as this spatial temporal matrix in the simplest case. So array geometry, waveform, and then also the actual architecture, so-called beamforming architecture. Here you see a so-called hybrid beamforming architecture where you have fewer digital channels than antennas. So this is known as hybrid beamforming, where you then kind of combine these antenna signals in judicious ways to kind of reduce basically cost and power consumption of these systems. And this is already in place in modern communication systems. Okay, so the key in these future wireless systems is to kind of, which are envisioned to have even more antennas, right, is really to make efficient use of all these resources. And here I will argue that the role of the array geometry is even more pronounced because of the introduction of sensing into the basic functionalities of these systems. Okay. So the talk is structured in basically two parts, more or less. So let's see how far we can get. First part is on so-called index or spatial modulation for ISAC. So this is a particular technique where we will show some interesting trade-offs between sensing and communications, and basically try to answer the question. So okay, this index modulation in this context means antenna selection. So you make actually you utilize the spatial dimension of your arrays to encode information in sensor subsets. Okay, this is known as spatial modulation, which is or generalized spatial modulation, which is a special case of this more general concept of index modulation. So there we will try to answer the question: what subsets of antennas are good for sensing, and how many are there of such subsets? Okay, and the second part will be a more conceptual talk. Let's see if we can get there. But basically, it's about an interesting connection between sensing on one hand and so-called subspace codes on the other. So subspace codes kind of arise in, for example, non-coherent communications, where instead of let's say code word being a point in space, it's a subspace itself. Okay, so this arises when you don't know the channel at the receiver and you don't even try to estimate it, but you can still kind of recover information from this subspace. Okay, and it turns out that in sensing, actually, information of interest is often encoded in the subspace as well. For example, in direction of arrival estimation, typically the range space of our measurements kind of course reveals the, let's say, directions of arrival. Okay, so this is the connection that we will explore in the second part. Okay, so here are QR codes. If you want to look up the papers, you will get the slides after the talks. Okay, so let's get started. This is joint work with two collaborators. So the first part with Professor Pia Pal from UCSD in the US, and the second part with both Professor Pal and Professor Esa Mahdavifar from Northeastern University. Okay, so part one, let's get started. The basic signal model I'll be considering here is this monostatic ISAC system. Monostatic meaning that there's a sensing transmitter and receiver are kind of at the same location more or less, so they see the same, let's say, angle of the targets that they're trying to sense. And then we have a communications receiver as well. So the downlink signal at this user can be thought of represented by this matrix Z, okay, where H is our channel, and S is the transmitted spatial-temporal waveform matrix, or block, you can think of it as. And similarly, for the sensing part, the backscatter signal can be represented as this Y. Okay, so we have G, which is a function of some parameters of interest, so think directions of arrival, again, times our S. So we see that this S kind of has a dual role here. On one hand, the task of the user, communications user, is to decode S. It doesn't know S, but so given H or an estimate thereof, tries to decode it. Whereas for the sensing part, we know S, right? Because we know transmitter and receiver are co-located for the sensing part at the base station. We know S, and we try to figure out this parameter fit our estimated. Okay? So this is roughly the setup. And the key point here is that now both the sensing, the waveform actually, S, and the transmit array geometry is common for both tasks, right? So, and this is our kind of two key quantities we will focus on. Okay, so how to choose them. And we'll in particular be looking at choosing subsets of transmit antennas, okay? And those will be, whatever subsets we choose, they will be kind of in common for both the sensing and communications tasks. Yes?
Here, one thing is that there's no self-interference, assuming it's perfectly cancelled.
That's correct, yeah.
And are you assuming that the same sensors or subset of sensors are used for both tasks, meaning that you have a set of antennas which are transmitting the signal and simultaneously the same antennas are receiving the signal, or you
No.
have a separate receiver?
It's a separate receiver. So only here I'm only assuming that the transmit sensors are shared by the two tasks. So yeah, it's like co-located transmitter and receiver doesn't necessarily mean that they have the same antennas. They just kind of are close enough to see the same angles. That's what I mean here by monostatic or co-located. Okay. Good clarifying question. Okay, so now. Well, receiver array, we'll get to that. I didn't make any assumptions on what the geometries are. So the goal will actually be to understand the trade-offs here in terms of, let's say, maximum number of code words I can generate by this subset selection, yet have a certain sensing performance, and that sensing performance will depend on the array geometries of both the transmitter and receiver used for the sensing part, okay? But yeah, I'll get back to that. So okay, sensor selection, of course, is widely considered in communications and sensing for a long time. But yeah, more recently, then in classical MIMO communications, there is this whole literature body of work on spatial modulation or index modulation more generally, where this idea is indeed, as I mentioned already earlier, to encode information in subset of antennas or let's say carrier frequencies, etc. So this is known as index modulation. So here are some works in the MIMO communications literature, and then also more recently than in this ISAC context, okay? And our focus will be basically answering the question, when we do this transmit antenna subset selection, are there some subsets that are better or worse for sensing, and how many such subsets are there? So the general idea is that the more of these good subsets we can find, the more basically higher rate we can achieve by this subset selection alone. Okay, so then you can have on top of that other modulation, like more traditional modulation or constellations as well. Okay, so there's a kind of gap in understanding this sensing communication trade-offs when employing these kind of form of index modulation. Okay, so just to illustrate what I've been saying here in words or in pictures. So imagine we have this three sensor transmit array. Then if I choose two antenna subsets, then there are these three possible choices, right? And these can each be thought of as a different code word. Okay. And why would people do this? Well, first of all, you would need fewer, let's say, digital channels or RF chains than antennas. So this can reduce power consumption, and you can actually compare to like, let's say, just doing classical modulation. You're now utilizing an additional spatial dimension, right, and encoding information there, so you can kind of improve your achievable rates. And yeah, so I won't go into too much detail here. I'll just refer you to, for example, these two excellent references for some basics on general spatial modulation. Okay. So now in our case, okay, the spatial temporal waveform can be kind of decomposed into these two parts, where we have our more, let's say, classical modulation symbols, and then this sensor selection matrix, right, where now this subset S of L kind of denotes the subset of sensors we choose at, let's say, time instance L, okay? And we choose Q of them, and then, right, each of these subsets of transmit sensors can be thought of as belonging to some sensor selection codebook C, okay? And then at the communications receiver, you can try to figure out what was this set of transmitted symbols, and then also the subset of sensors used, knowing the channel. This is the basic idea, okay? So we'll make a simplification here, which is considered in some of the more let's say, sensing-centric or radar-centric literature, where we just encode over, we just focus on sensor selection, so the X part, actually, modulation part would be known. That would be, for example, selected some set of orthogonal waveforms, okay? This is typically done in MIMO radar. And then we're just encoding over this set of selected sensors, right? And we're doing this over a bulk of basically samples. So it's kind of slow time, over slow time. So just we're going to do the simplification to get some insight into the problem. Now, under this setting, basically, environments, you don't really have any preferred directions in a sense, or any preferred sensors on average, right? For a given realization of the channel, sure, some sensors might be better than others, but on average, there is no one sensor isn't preferred over the other, okay? But in sensing, it's quite different because there, as we'll see next, the channel has a quite different structure, right? The geometrical structure depending on the array geometry and these angles of arrival. So there, actually, I'll argue that not all antenna subsets are created equal, okay? For example, in terms of identifying as many targets as possible, right? Okay. So how many? Then we'll try to answer the question, which subsets are good for sensing and how many are there? Okay, because we want to have as many as possible, right? For basically increasing our, maximizing our rate, let's say in the high SNR regime at least. Okay. Okay. So this is a canonical model for the sensing channel where basically we have these array manifolds AD and ADT and ADR, where DT and DDR refer to the transmit and receive manifolds respectively. We have some scattering coefficients which are unknown. These represented by the gammas here. So this is a basic far field model, right, where we transmit, illuminate some targets far away, active sensing far field model, and we receive the backscattered radiation. And if you look at the entry of this sensing channel matrix, it will basically be a function of the sum of transmit-receive sensor position pairs. Okay, so that's represented here by this DTM and DTR. That's a pair of transmit-receive sensor positions, right? So you can think of it as like locations here of these sensors. So this is known as a sum set or virtual array in the jargon, co-array also, some co-array. So this is just set of all possible transmit-receive sensor pairs, denoted here by d sigma. And just to visualize it, here are three different array geometries where I vary the transmit array geometry with a fixed ULA receiver. We end up with three different kind of virtual sensor arrays, okay? And here, basically, the distinguishing feature about this virtual array is that some of these virtual elements can overlap. That means that basically you have two or more possible transmit-receive sensor pairs giving rise to the same virtual element. So for example, here, 0 plus 1 or 1 plus 0 equals 1, right? So there's the multiplicity 2. Okay, this is known as array redundancy. I won't go into detail about what is optimal array redundancy, but there are, let's say, certain benefits of also having. So you would, first of all, you would typically see these non-redundant arrays in MIMO radar applications where you want to identify as many targets as possible or increase resolution. Whereas then actually, many times when you want to do beamforming, for example, you would tend to see these more like ULA kind of arrays, which are very redundant or actually maximally redundant because they have well-behaved beam patterns. These are just one reason for having a redundant array versus a non-redundant array. Now, the sensing criterion that we'll be focusing on will be identifiability. So that just in simple terms means that when can we, given our measurements, noiseless measurements, recover the parameter of interest? Because if we have a measurement which is ambiguous in the sense that it could have been given rise to by two different values of theta, right? Then there's no way, without a priori information, we can distinguish between the two. So identifiability just means that there's a unique mapping between theta and y, okay? And it's kind of well known that you can identify up, so if you have a sum co-array of size, basically n sigma elements, and they are kind of form a uniform virtual array, then you can identify up to n sigma over two targets, okay? And this is kind of the maximum identifiability, okay? So now we can formulate our question a bit more precisely. So we want to characterize which of these NT choose Q possible subsets of transmit antennas will give rise to basically some set, right, which is equal to this virtual array of size n sigma. Because that will guarantee that each, no matter which of those subsets we choose, if they satisfy this criterion, then we will kind of we can show that it will maximize identifiability or enable us to resolve as many targets as basically using the full array, okay? Okay, so again, I want to just illustrate this in a picture. For example, here, choosing 3 antennas out of 4 transmitters with then say, virtual array of size 7 elements. We have these 4 possible choices of 3 sensors, right? And if we look at the sum set, only 2 of them have like the same sum set as the full array. So these 2 in the middle. So if we don't select the first or the last element in this case, yeah, we can see that. So we wouldn't like to use those 2 subset selections for sensing. We would like to use only the 2 middle ones, okay? Yeah, now I'm just okay. So for the communications part, I argued that there is no preference in which subsets of sensors I use. So I would just use all of them. If I just did the communications, then I would maximize the size of my code book by just looking at using all NT choose Q possible subsets. Yeah, that's true. That's true. Yeah, that's correct. But on average, yeah, over all a priori. But here I'm saying also a priori for sensing, without knowing what the realization is. If I don't select these certain sensors, then there exist realizations of the channel for which I cannot resolve unambiguously the thetas of interest. So I will get back to basically, now I will argue that with this constraint, if I ensure that whatever code words I choose, whatever subsets I choose, I have this identifiability criterion, then yeah, that will be at least, let's say, upper bound on the number of subsets of transmit sensors which I can use for this sensing and communications jointly. So yeah, for a given realization, yeah, they might be smaller, but this is at least a kind of upper bound if I want to guarantee. Yeah. So basically, compared to the communications only setting, I'm now reducing actually the number of basically code words. So I'm taking a hit in rate, and then I want to characterize how large of a hit am I taking, okay, as a function actually of this number of identifiable targets. That is what I will ultimately get at. Okay, so now I can formulate the optimization problem for basically, yes? Yes, indeed. So this is, and you kind of touch upon also another aspect. So uniform versus non-uniform identifiability. So here I'm talking about uniform identifiability, which means that regardless of what the ground truth is, I can guarantee that I can identify it, right? Non-uniform identifiability again means for a specific problem instance, can I or can I not uniquely identify that given value of theta, right? So here, well, no, this is fundamental. I mean, regardless of whatever algorithm you use, if you have a non-identifiable situation, then I mean, without any a priori information on the target directions or target amplitudes, no algorithm will be able to unambiguously resolve. Then there's, of course, you're referring to then different algorithms might have different ambiguity issues, right? And that's another issue, but this is more fundamental in terms of this is algorithm independent identifiability that I'm talking about. So no matter what algorithm you choose, if it's unidentifiable, then yeah, there's nothing you can do.
Also, back to what you're saying, it also depends on the, say, the rank of S. So, I mean, I can still have a full array, but okay, a low rank S, then
Yeah,
right.
right. So here I'm absolutely, yeah. So here, the kind of implicit assumption was, or I said it explicitly, was that this X, right, that will be full rank. So that means actually that the rank of my waveform will be now Q, which is the number of transmit antennas I select. So in that sense, I will assume that I send independent, let's say, streams from each selected antenna. Now, and indeed, n sigma now will cap the number of targets I can simultaneously identify, uniform identifiability guarantee. Okay, so that's the kind of relationship between the two. Now you might be able to go on beyond this n sigma over 2 for a specific problem instance, right? But yeah, there exist configurations of targets which you cannot identify. So that's what this uniform identifiability guarantee means. So whatever the target configuration, I can guarantee that I can identify up to this many targets. Okay, so now I just, to wrap up this part, I will just say a few words about the actual optimization problem then that I'm interested in so characterizing. So we can first characterize this code book of transmit antenna subsets of cardinality Q, which have the same sum set as the full array, okay? That's what I denote here by C superscript S. And now I want to find the code book optimize over the transmit and receive arrays for a given number of physical transmit-receive antennas and then virtual antennas, right, which determines my identifiability, as I argued before. So I want to optimize over these receive and transmit arrays and also the code book to give me the code book of maximum cardinality, okay? Okay, because that will give me the largest number of code words that I can, basically because my rate will be proportional to the number of code words at highest NR, okay? So this is the combinatorial problem that I want to solve. Of course, I'm not saying I can solve it. Just to kind of, again, remind you that in this code book, if I were to be able to find it, it kind of can encode log 2 cardinality of C star bits and guarantee the identifiability of n sigma over 2 targets, okay? So this is the nature of the code book that I'm trying to find. Of course, this is a combinatorial challenging problem, so I don't know what the solution is, but what we can try to do is find some upper and lower bounds on the cardinality of this set, okay? And that's what I'm kind of spend the last few minutes to show you some preliminary results there, okay? So we can think of this size of this code book versus the, let's say, number of identifiable targets or size of sum set as this figure in this pictorial manner here. So at the moment, I'm very ignorant. I don't know what this curve looks like. So this blue region represents my region of ignorance in a sense. So I want to narrow this down now to get something meaningful, okay? So first we can argue, when is this set non-empty? Well, the possible values of n sigma actually range between the fully redundant and non-redundant cases. Okay, so between these two values, that's kind of easy to show. And then there's also a smallest value on the number of transmit antennas I need to select in order to ensure that the sum set of that subset equals the sum set of the full array. Okay, and this quantity is this ratio between n sigma and nr. Okay, so this can also be kind of argued because otherwise, yeah, basically there's no way that the sum set will be of sufficient cardinality. Just as a side note, this is actually interesting. Refers to Sandeep's question here about the rank of the waveform. This kind of can be thought of as the minimal rank of the waveform matrix S, which we need to have full identifiability. Okay, maximum identifiability for this given array, or n value of n sigma. Okay. For more details, you can look up at some of our other recent work. Anyway, so now basically with these two constraints, or let's say on n sigma and the number of transmit sensors we select, we can kind of narrow down now this region of ignorance a bit. Okay, so now basically this region we gained. Okay, let's see if we can do better. So an upper bound on the cardinality basically comes from figuring out some necessary condition that any subarray must satisfy for the sum set to be, let's say, maximum size. And that is, which you kind of saw already earlier, that you need to select the first and last transmit sensor, because those actually give rise to a virtual element of redundancy 1, so there's no redundancy. So if you don't select that first transmit sensor, then basically the first virtual sensor will not be there. If you don't select the last transmit sensor, the last virtual sensor will not be there. So this you can show. So basically there are two sensors in every transmit array that you have to always include. Okay. So this gives you this upper bound on the cardinality of this optimal set. Okay. And actually, interestingly, although this is kind of seems like a trivial thing, you already get tight characterization of the two extreme points. So namely the maximally redundant array, where both transmitter and receiver are ULAs, and the non-redundant array, where there's basically the number of virtual elements equals the product of the number of transmitters and receivers. So these two cases shown here. Okay, so I'll show that here. So for the ULA, really the cardinality of this set is exactly this, nt minus 2 choose q minus 2. So there are many code words, in other words. And for the non-redundant case, basically, when n sigma equals the product of the number of transmitters and receivers, the cardinality of the codebook is just 1. Because if you don't select any one transmit antenna, then you will have you will be missing a virtual sensor. That basically just comes from the definition of what non-redundant means. So this means that a non-redundant array, if you want to basically identify many targets, then you cannot afford to not select any transmit sensors. Kind of makes sense. In the case of ULA, you have a lot of redundancy, so you can actually afford to, not select quite a few sensors. Right? This is what it means. Okay. So pictorially, for the ULA case, this is just, basically what I'm saying in words. That you can kind of select these first and last sensors under some mild constraints on the number of sensors, transmit and receive sensors. Then you still get the full virtual array. Okay. So this is already indicative of a trade-off between identifiability and codebook size. Okay. So let's go take one more step and try to get a lower bound on the cardinality. And this comes from just a construction, right? So if we can construct any given, let's say, scheme for selecting transmit sensors and then guaranteeing, just showing that we will still have full identifiability, then that will give us a lower bound, okay? So now, basically, I'll be arguing that we have this kind of lower bound on the cardinality of this optimal codebook. Basically, nt minus l choose q minus l, where l is now this ratio between the number of virtual elements and number of receive elements. And basically, yeah, it's by constructing this kind of set of transmitters and receivers where I can always choose this set of L sensors such that I have kind of a non-redundant subarray. Okay, and then the rest of the sensors I can either include them or not, right? So this gives me the lower bound, a lower bound. So this is just based on a kind of nested non-redundant subarray structure. Okay, and now our region of interest, ignorance has reduced quite dramatically. So these are the upper and lower bounds on this optimal codebook size that we end up with. And of course, these can be tightened further. I just want to, one more thing, kind of give you a preliminary sneak peek into answering the question of how to choose the number of transmit sensors then optimally, the number of basically Q. Here it was a variable up till now, but I can also think of optimizing over Q. And basically using the bounds we had, we can kind of get this kind of upper and lower bounds, which is basically shows you now the ISAC trade-off between identifiability and codebook size, right? So the more targets we want to identify, the smaller the codebook size, vice versa. The fewer targets we kind of need to identify, we can kind of have a much larger codebook, and hence, which translates into rate in communications. Okay. So yeah, of course, this canon should be tightened further, but yeah, just to wrap up this part, what we basically showed was ISAC codebook with identifiability guarantees, and kind of quantified actually this trade-off preliminarily. So yeah, if you want further details, here's a QR code you can scan or look this up on archive. So that's the first part. Any other questions? Thanks for the many questions so far. Any further questions from the audience before we move on to the second and final part? Yes?
If I recall correctly, some papers in ISAC, they consider the reflected signal as some component of H.
Right. So here G, the sensing channel matrix, and H, the communication channel matrix, were kind of decoupled. Okay. Right, so they didn't, but you're exactly right. I mean, this is, I think, the core interesting question in ISAC when the two share parameters. Because indeed, I mean, you can, if you have some target reflector, then probably, if it's, your communications channel will also see some of those reflectors, right? So indeed, then I think that's an interesting coupling between the two problems, which here I did not explore, right? Here I just assumed that basically I said that the H is like the typical Rayleigh fading model. But yeah, excellent point. Right. Yeah. It's
so how does it change, for example, if you have a structured channel, or because the design now is completely ignorant of the channel that the communication receiver is seeing.
Yes. So that's a good question. So basically, at the moment it's ignorant of the channel and basically not assuming any structure in the communications channel. That's correct. So that's kind of future work. And the first part of your question was related to, I already forgot. Right. The rate. Okay, right. Yes. So, yeah.
Also means that you're stretching the rate.
Yeah. So this cardinality of the codebook is, of course, a very rough measure of maximum achievable rate at high SNR, right? When you have finite SNR, of course, you may want to actually reduce the size of that codebook further, right? For example, optimizing something like minimum code word distance in some suitable metric. So that is completely ignored here, right? So that is a very interesting, I think, direction of future work as well, to characterize this trade-off at finite SNR and using some other metric than just the size of the code book, right? So there are some works like this I mentioned this work by Nostratina, where actually they kind of try to address this in a communication-only setting, right? So there's a kind of sweet spot between.
Here you would like to go towards, so now you're going towards north east, but then you would like to go towards communications, you would like to go towards southwest.
Right, I mean, yeah, you would like, yeah. So I'm not sure I quite understood. I mean, yeah, you would want to hear for the communications part, you want to be like as high as possible, right, in the cardinality of the sumset, at least for this high SNR. For lower SNR, yeah, that's an open question. I can't answer that. What is the optimal size of the codebook? I mean, it will be a function of SNR, right? That much we can kind of infer. But what exactly the function is, yeah, I don't know. But so I think is a good research question. Yeah. Okay. Any other questions from this part? If not, I will proceed to the second part, and I will try to make this brief to stick to the schedule. So basically here, long story short, is in sensing, often the information of interest, like in directional arrival estimation, is encoded in a subspace, in basically the range space of our measurements, right? And there is some interesting connection that we kind of started exploring recently between sensing on one hand, on the other hand, so-called subspace codes, which are kind of considered in various contexts, but for example in non-coherent communications where information is encoded in a subspace rather than a point in space. Okay, so we're excited to start exploring this and making basically building bridges between these two communities, which have been kind of separated so far. Okay, so just to pictorially again illustrate what I mean by subspace codes. Traditionally, we would think like if we have, for example, a 16 COM, you can think of these as points in space, right, in a complex plane. Now, if we don't know the channel at the receiver, and we don't even try to estimate it, can we still transmit information or recover, basically, transmit information to the receiver? And the answer is yes, by so-called subspace codes, by basically encoding information in a given subspace. So here in the one-dimensional case, you can think of these as lines, right? So then the question becomes one of packing lines in an efficient manner. Okay, and this has been studied also in applied mathematics, known as basically Grassmannian packings, as I'll kind of mention here later. So this kind of suggests now that there is a connection between these two worlds of sensing on one hand and subspace coding on the other, and that's what we kind of want to explore. Okay, so just to give you a brief kind of idea about the body of works out there in these two separate kind of domains. As I mentioned, packings in Grassmannian space have been studied for a long time, already by Shannon actually. So Grassmannian is just a manifold or collection of subspace of a certain dimension, right? All possible subspace of a certain dimension, and they typically want to pack them in a way that you minimize the basically angles between these subspaces. Okay. In non-coherent communications, I mentioned that's another application. Limited feedback beamforming. There have been some works early 2000s, and basically more recently in network coding and analog subspace codes, where basically these were extended by my collaborator into basically real and complex domains, where classically, the subspace codes were over finite fields. Okay. On the other hand, in sensing, we know that high resolution DOA estimation methods like subspace methods, right? They try to identify a subspace, or even maximum likelihood estimators. They really work with subspaces, try to find a subspace. Simultaneously, there have been very recently a lot of research into sparse sensor arrays, which kind of the basic idea is that you can by distributing your sensors in a judicious manner over a larger aperture, or vice versa, reducing the number of sensors in a judicious manner from a uniform array, you can identify more targets than or sources than sensors, or improve resolution on the other hand. And then, of course, this has become like even more, as I tried to argue in the beginning of the presentation, more relevant in this emerging and future wireless systems, ISAC systems, where resources are shared between both communication and sensing. Okay. So then the question here is, how are these two kind of separate domains linked? Are they linked, and how? Okay, and I'll argue, of course, that by a subspace codes, or by the perspective of the subspace, they are. Okay. So let's establish a simple signal model here of this canonical passive sensing model, where we have a bunch of sensors observing some far field plane waves impinging on the targets, or superposition of plane waves. So this is the received signal model, where we have like these complex exponentials basically denoting or modeling the angles of arrival, right, multiplied by some unknown source signals x. So we don't know them, but we don't really care about them when we're interested in the thetas. And we want to recover these thetas by the directions of arrival without really knowing what x is. Okay. Okay, and I will show that this is basically a subspace, can be interpreted as subspace coding or decoding problem, actually. So to establish some notation, let's define this message of interest, u, as just this vector of DOAs, right? So, by the way, I just mentioned that for simplicity, we consider an on-grid model, so where these sources come from some predefined grid, right, to make this connection more obvious. Okay, so now we have like a set of angles coming from this grid, and we want to figure out which of these messages or set of angles we observe. Okay, so in matrix form, we can write this measurement as this h times x, where h now, the columns of h contain the message of, or encode the message of interest. The angles, that is. X is unknown matrix. We'll assume it's a full row rank, and W is a noise term. Okay. Okay. In contrast to, let's say, communications, here actually the message is produced by nature, as is this basically X, which would typically be the channel in the communication setting, and both are unknown. And just mathematically to show once more what I mean by the range space of basically our measurements encoding the information of interest, if we look at the range space or the column space of our H matrix, right, when we have full rank X, basically it's the same as H times X, right, the range space of X times H times X, and in the noiseless case, this is exactly the range space of our measurements Y, okay. And now we'll look at so basically the structure of H now is determined by the physics of the problem. So it has this complex exponential structure, right, where each column corresponds to a given theta, the given direction of arrival, shown here, okay, just to refresh your memory. So there's this kind of harmonic structure in the problem. And now the basic, let's say, tuning knob we have is this position of the sensors, right? So this is, again, denoted by this D subscript M here for the mth sensor. So this is what we can tune to change the code, right? Otherwise, it has this structure. Okay, so this is okay, just an illustration of the sensing geometry can look something like this, and of course, in hardware, we would implement it as an antenna array or sensor selection. Okay, this is, I think, clear to the audience by now. And then we can define sensing subspace code as a set of basically all possible subspaces induced by our possible messages, right? So this denotes the range space of H, right, which was channel matrix or sensing channel, and where H now obeys this structure, complex exponential structure I showed before. So we can interpret basically this as a very highly structured subspace code book, okay? Where the structure now derives from the physics of the problem, right? Okay? So this establishes the connection between sensing and subspace codes on one hand. And then, okay, so that's the kind of main message, that there is this connection. And now the question, of course, the natural follow-up question is, so what can we do with this? Okay? Now, what are kind of good sensing subspace codes, and how do they translate into, let's say, sensing performance array design? Okay? So the basic message is that by this perspective, we now have a kind of principled new way of designing array geometries for sensing, right? Where actually we'll see that the typical metrics used in this to design these subspace codes is distances between subspaces, and that hasn't been considered before. So that's something we're very excited about, to design new array geometries based on this, maximizing this minimum subspace distance, for example. And on the other hand, for subspace codes, well, this gives a new family, let's say, of subspace codes, which, you know, I don't know, I think it's still an open question what the applications are for these subspace codes, but with this specific structure of induced by the sensing physics, okay? So I'll just wrap up by considering a special case. So case of one source, and we can say some interesting things about that and get some insight into these designs to get a feel. The general case of subspaces of higher dimensions is still ongoing work. Okay. So I mentioned already that the typical metric for designing these subspace codes is subspace distance. So that's just basically principal angles between these subspaces, okay? And in particular, you want to typically maximize the smallest angle between any given pair of subspaces, right? Because that will be kind of the bottleneck in your, that will be the most difficult, let's say, in the sensing sense, the most difficult pair of thetas to distinguish between, okay? Yeah. Yeah, so that comes in the structure of H, right? So H now, if we look at, yeah, so you will, depending on how you design your array geometry, that will define your code book, right? So now, basically, if you want to optimize for example, this minimum subspace distance, that's a metric for optimizing your code book, then you do that via designing your array geometry. So different array geometries will give you different minimum subspace distance, for example. So the tuning knob here is the sensor positions here shown in this expression for the elements of H. So that will, of course, define then what set of subspaces does your code book contain, and what is the distance between those subspaces in particular.
So whenever there's no sensor selected, you still keep the 0, or can you shrink the vector?
So the same set of sensors are used for all code words, right? But basically, the variation now comes from the set of possible angles, right? So if I have, let's say, a grid of n, size n, and I choose k, so I have n choose k possible choices of angles. So that will basically, those are the number of subspaces that I need to consider. And now the array geometry will influence, of course, what the distance between those subspaces are. Did that make sense? Yes. Yes. Yeah. That's the basic setup of the problem, but of course one can go for it. So anyway, this basically it can be shown that this maximizing this minimum subspace distance can translate into a smaller probability of decoding error for example, maximum likelihood decoding, and in particular then smaller MSE. Okay. Okay, so in this single target case, actually this minimum subspace distance has some very interesting structure. Okay, if you look at it, maximizing the minimum subspace distance for one source actually can be written as minimizing the maximum of this sum, where minimization happens over the sensor array geometry, right, the set of DMs, and maximization happens over the angle. Okay. And this is actually nothing but the beam pattern of the array sampled at the grid points, right? So beam pattern here is shown in blue, and the red dots represent the sampling points. So basically, we want to kind of minimize the maximum side lobe level in some sense. That's how you can interpret this. So if we have array geometries with low side lobes, at least on the grid, but of course more generally anywhere here in the side lobe region, then that will give us a good subspace sensing subspace code, at least for one target. Okay, for multiple targets, yeah, it's more complicated. So this is one nice connection to the beam pattern and between the beam pattern and the minimum subspace distance. Okay, and there's also an interesting connection to difference sets, right? So, which we can see by just opening up the square, which was in the objective function, right? This is what the minimum distance depends on. You can see it depends on actually the differences between these sensor positions. This is known as the difference set, which is now illustrated here. So excluding the self differences, the difference set of this set of sensors looks something like this. And in particular, yeah, different sets arise. This is kind of surprising because here we have no assumption of uncorrelated sources or anything like that, which is the typical context in array processing where different sets arise. Of course, frames or these kind of subspaces, line packings with harmonic structure has been considered in a different context, but yeah, okay, that's correct, but that's still different from assuming that you have uncorrelated sources. Yeah, but yeah, you're right. Full row rank X is an assumption, but yeah, still, typically, if you look at the second order statistics of and assuming uncorrelated sources, then yeah, you get this difference set, but this is not the case here. So it's different in that sense. Okay. Okay, so then if we have a, let's say, grid size which is much larger than the number of sensors, how to design these sensing subspace codes. I won't go into details here. I just say that, okay, we have some constructions which we can show basically based on Golomb rulers, which we can show analytically achieve like almost optimal subspace distance. So basically achieving the Welsh bound, which is in this case gives us a upper bound on the minimum subspace distance. So we achieve that kind of order-wise with these kind of Golomb ruler-based designs. And similarly, you can show that uniform arrays will not work in this regime where your grid size is much larger than the number of sensors, but it will give you a poor subspace distance, in particular not converging to 1, which is the maximum value basically of this subspace distance. So just to show you some simulations, here is the subspace distance plotted as a function of the number of antenna elements. So for this sparse array designs, basically this Golomb rule, Bose-Scholar ruler, basically we have this subspace distance converging to 1, which is the maximum value, whereas for the ULA, it kind of decreases, goes to 0 actually. In terms of probability of error, you can analyze the maximum likelihood decoder, or which is equivalent to the minimum distance decoder in this case, and show that it depends on this minimum subspace distance, right? This is an upper bound, okay? You can similarly show for a lower bound, and here plotting the probability of error as a function of SNR and number of sensors, we can see basically this drop in the probability of error in case of the sparse array design versus then the ULA, both the empirical lines and then in the dashed, the upper bounds that we derived, okay? So basically, we have basically mapping between or we have constructed sparse arrays, which gives us a good minimum subspace distance and translates into low probability of error and mean squared error actually implicitly. Okay, so that's basically a summary of this paper, and if you want to see more details, please look into scan this QR code. But yeah, we were excited to now basically connect these two communities in coding on one hand and sensing in the other, and explore the connections between these two worlds, and basically explore the implications also, of course, in the sensing an array design based on these subspace distances, which is completely new. Okay. And I just want to end with a advertisement. So for any prospective students or postdocs, yeah, if you're interested in, if any of this work piqued your interest, then please reach out to me. There's also some open postdoc call at the moment in my university in Tampere, Finland, so pictured here. So yeah, you have access to the slides after this talk. So yeah, please check out this link. And if you're interested in a postdoc, then please apply before March 2nd. So it's pretty soon. But yeah, if you're interested in doing a PhD, then yeah, reach out to me, please. With that, I'd like to thank all of you for your patience on a Friday night. I really appreciate it. And thanks for the many questions so far. And yeah, if there are any further questions, I'll be happy to take them. Otherwise, thanks. Thanks a lot.
Thank you, Professor, for accepting our request to deliver a talk at our the late time, and also for the advertisement. It will be helpful for many of us. Okay. In the interest of time, we will take only 2 questions, if there are any.
So when we write e power something times sine theta, and when we start talking about different sets, now this exponential, complex exponential, wraps around at 2 pi. And so when you start taking these differences and you have these very long differences, at some point it wraps around and there will be an ambiguity that comes up because of that, right?
So exactly, that's a good point. So here, actually, what we're looking at is not the difference set itself, but actually difference set modulo n. So that's why you see here's the difference set, and then modulo n, you get actually this almost uniform, non-redundant actually difference set, and that's kind of what allows us to argue then that the subspace distance of this is favorable. Yeah, but excellent point.
But physically, it's actually a delay, right? It's how far can one think of a delay as a phase shift? Right? It depends on that as well.
Delay.
For small delays, yes, small delay can be approximated as a phase shift, but not very large delay. And you have to actually think of it as a delay.
Right. If yeah, okay, I see. So basically, you're saying that yeah, this implicit approximation of, let's say, a time delay is a very narrow kind of bandwidth being approximated by the phase shift. Yeah, if the array is very large, then of course that doesn't hold. Yeah, that's a fair point. I mean, that's not something I address here, but yes, that's correct. If you have a very large array, then yeah, the kind of far field gets farther and farther away. So yeah, at some point, yeah, if you will end up in the near field, and far field assumption or approximation won't hold. True.
But then that as you
Yeah. Yeah, I mean, here, in terms of the difference set, I don't think it matters, but yeah. So if it holds, let's say, for the physical array, then it will hold for the difference set as well. But yeah, of course, if the physical array is very large, then you might run into this physical trouble with the assumption. Yeah.
Yeah, rather than the near field versus far field, it's more related to, I think, the beam swing type, beam swing, beam split type.
And this is bandwidth. Yeah, this is again bandwidth issue. Yeah. Yes. Yeah. Yeah. Basically, right. So it's a narrow band assumption, basically, if it holds or not. Yeah. You're right. Yeah. Okay. Any other questions?
I guess Professor has answered all of your questions.
I don't know, but you can send me or chat with me offline or send me an email if you think of anything. But yeah, thanks again for your attention and for the many questions. Yeah, I appreciate it.
Please, sorry.
No.
If you want to connect with Professor, please do so with some refreshments in the coffee hut. Thank you all and have a great evening.